In low-mass stars, hydrogen fuel in the center begins to run out as helium content increases. The rate of hydrogen burning in the shell surrounding the core will cause the star to bloat into a red giant. The core of the star eventually reaches a high enough temperature to fuse three helium nuclei to form a carbon nucleus. Oxygen and carbon accumulate until the electron degeneracy pressure that normally counterbalances gravity becomes insufficient, causing the red giant to push its core electrons out and causing it to shed its outer envelope and create a planetary nebula with a white dwarf in the middle. An iron core accumulates until the electron degeneracy pressure that supports it against gravity becomes insufficient and the core collapses inward, causing an explosion called a supernova. What is left over is a neutron star, which are some of the smallest and densest stars known in the entire universe. The largest and hottest stars in the universe burn hydrogen, helium, carbon, oxygen, and silicon as fuel. Just like intermediate mass stars, an iron core forms when the core's resources become depleted. Gravity then causes this dense core to collapse completely in on itself. When the core collapses, the gravity is so strong that even neutrons are insufficient to resist the condensing of matter, and the core transforms into a gravitational singularity where one point contains all of the mass of the entire original star. This is a black hole.
Well, what exactly is a black hole? How do they work? Well, we titled this video, What Happens in a Black Hole Stays in a Black Hole. Why? Are black holes exclusive? Of course not. Black holes work by way of a concept called escape velocity. So if you really hate living on this planet, here's your guide to getting away. Escape velocity is the minimum speed that an object needs to escape the gravitational pull of the massive body on which it resides, and to never return to it again. But how much speed would you need exactly? Well, for a spherical body such as the Earth, you would use this formula to calculate your velocity. At the Earth's current mass and radius, it would take a velocity of 11.2 kilometers per second to escape the gravitational pull. But what if the radius of the Earth was smaller, yet it had the exact same mass? As the Earth becomes smaller and smaller, and the radius shrinks, the speed that you would need to escape the Earth's gravitational pull grows faster and faster. For instance, at 1/100th of the current radius, you would need a speed of 112 kilometers per second to escape the Earth's gravitational pull. Eventually, the radius will grow so small that the speed that you would need to escape the Earth's gravitational pull will be faster than the speed of light. This radius is called the Schwarzschild radius, and we calculate it using this formula. But wait, what's faster than the speed of light? Nothing. So now we've answered the question of what is a black hole. It's clearly a body whose mass is so large but radius so small that the velocity it takes to escape this body is faster than the speed of light, which is exactly why what happens in a black hole stays in a black hole. Nothing is faster than the speed of light, so nothing can escape a black hole.
In his theory of general relativity, Einstein states that space and time are related to one another and must be considered together. Massive objects in space are related to time in that the heavier and more massive an object, the more it warps the space around it. And black holes are incredibly dense and massive. Even though a black hole has all of this condensed matter, it is unobservable because we are unable to see past the event horizon of the hole, which is what we see on the outside, because relative to us, time is frozen at the event horizon. The Earth, for example, has a mass that bends the space around it in our solar system, creating ring-like orbits around the object. Gravity is thus formed, and other objects, such as our moon and satellites, can follow a continuous path around Earth, held in place by the gravity made in relation to Earth's bending of space. A strong presence of gravity also affects time in space. It is proven that time actually slows in the presence of gravity, and scientists use atomic clocks to test this. For example, time runs slower on Earth than around the orbit of Earth because of the stronger presence of gravity. Clocks on satellites orbiting Earth have to be slowed in comparison to our time so that we can receive accurate readings for systems such as GPS. In essence, some black holes are considered as time machines. If humans were able to travel in a spaceship around the orbit of a black hole without falling in, they would spend less time around the black hole than as observed and felt on Earth.
Question 1. What would happen if someone fell into a black hole? What would the faller see? What would the faller look like from an outside perspective? Ignoring the fact that a person sucked into a
Created using Powtoon.